In this video, we're going to look at matchings and the maximum matching algorithm. To start off, we're going to look at some graph theory and consider bipartite graphs. We're told here Granny has bought 5 CDs as Christmas presents but forgot to put people's names on the presents after wrapping them. She bought CDs for Mum, Dad, Tom, Charlie and Sam. The CDs were One Direction, Whitney Houston, Elvis, Jay-Z and Iron Maiden. We're told Mum likes Whitney and Elvis, Dad likes Iron Maiden and Elvis, Tom likes Elvis and Jay-Z, Charlie can just about listen to One Direction, and Sam likes all but One Direction. We're going to use a bipartite graph to model this situation. A bipartite graph has 2 sets of nodes, so we might have set X and set Y. In this case, set X might be the family members, set Y the CDs. Vertices in one set can only be joined to vertices or nodes in the other. So for example, now we would join X with Y. We wouldn't join X to X. Charlie joined to Sam makes no sense. We want Charlie to a CD and Sam to a CD. So let's go ahead now and model this. So what I'm going to do is add nodes or vertices in a straight line. Often bipartite graphs are not obvious to see. We can tell that they're bipartite as we will have simply now X's going to Y's and Y's going to X's. We won't have Y's going to Y's and X's going to X's. But generally, to show these, we put these now in a straight line. Often in the exam you'll be given a template, but as I don't have that, I'm just going to do this myself. So let's now just copy these across and we will now have 2 sets of nodes or vertices. So here we go, over and put these here. I'm going to use the first letter of each name. We've got now M for Mum. If we had now Mark as well, we'd have MU for Mum, MA for Mark, or something to distinguish between the 2. So we've got Mum, Dad, we've got now Tom, Charlie and Sam. So let's write those in. Tom, Charlie and Sam. For CDs that we've got One Direction, we've got Whitney Houston, we've got Elvis, we've got Jay-Z and we've got Iron Maiden. What we're going to do is use this bipartite graph to now show the links between these. It's really tempting to say the matchings between these. These are not going to show matchings just yet. A matching is a 1-to-1, and later in the video we'll see the difference. All we're going to do is use a bipartite graph to model this situation. When I do this, I'm also going to put it in a table. I also like the option of a table. You certainly don't have to, but you might see that when you're doing the maximum matching algorithm, it actually helps you out. So this is the person, and this is the CD. So if we were to do this with a bipartite graph, we can see that Mum likes now Whitney and Elvis. So there's Whitney and there's Elvis. I'm not linking Mum to Dad, I'm not linking Mum to Tom, I'm simply now linking X to Y. So in my table now, I'm going to put here that Mum likes now Whitney and Elvis. So they're 2 possible choices. We're told that Dad likes Iron Maiden and Elvis. So we're going to now put those on. So Dad likes Iron Maiden and Elvis. There's Elvis and there is Iron Maiden. The reason I like a table is often this can get quite crowded and I like to think about it now, seeing which ones we've definitely got. So this is a bipartite graph and this is a table. So this isn't part of the bipartite graph, I'm just doing it to help me. So we've got now E and then we've got I. If we now look at the next one, we're told Tom likes Elvis and Jay-Z, which is pretty diverse, but never mind. So we can see Elvis is pretty popular, so Tom likes Elvis and Jay-Z. So what we're doing is just now adding these to the bipartite graph. So Tom likes Jay-Z and Elvis, so let's put J and E. And we've got Charlie can just about listen to One Direction. I'll assume then that they would be happy, I don't know if happy is the correct word, they would accept the One Direction CD. So let's put Charlie, so Charlie, One Direction, and great Christmas, hey? And then Sam likes all but One Direction. So we can now put Sam on, and Sam can go to Whitney, Sam can go to Elvis, Sam can go to Jay-Z, and then Sam can go to Iron Maiden. So as you can see, that's fairly crowded. But this now is representing a bipartite graph. So we've got Sam, and Sam will just about do anything but One Direction. So W, E, and then J and I. So This isn't yet a matching, it's just showing us one possible configuration here of a bipartite graph using the information that we're given. So let's actually now move on to matchings. A matching is one-to-one. So for example, mum and dad both can't have the Elvis CD, as we need to match one node in X with one and one only in Y. A matching is a one-to-one pairing. It doesn't have to be all of the nodes. It could simply be now Charlie now to One Direction. That would constitute as a matching. That's not a complete matching, but it is a matching. We've matched now one node in X with one in Y. So if I wanted to show an initial matching, I could say C with O. So M with W could be another one. So I might want to draw a bipartite graph. I'm just going to go over the top of this now just to show that we might have an initial matching now of Mum to Whitney, and we would have now Charlie to One Direction. That is an example of a matching. It's quite clearly not a complete matching, but it's one possible matching. A complete matching is where we match all of the vertices in X with one and one only vertex in Y. Later in the video, we will look at the maximum matching algorithm. Now, we could, with this small set of data, just go ahead and try one. We could just go along this and kind of do it by trial and error. So let's have a look. I'm going to leave Sam alone, as he or she is quite open to this. So let's go down the list. So if I gave Mum the Whitney one, she would be happy with that. If I gave Dad the Iron Maiden one, he would be happy with that. Tom can handle Jay-Z. Poor old Charlie with One Direction, and that leaves me now simply giving the last one here. We'll give Elvis to Sam. This is one example of a complete matching. I've just gone through that. So if I wanted to do that, we could show a complete matching on the graph. Usually I'll draw another one, but as you can see, it's quite time consuming. I'm not going to do that. So what we could do now is match Mum with Whitney. We could match Dad with Iron Maiden. We can match Tom with Jay-Z. We can match Charlie with One Direction, and we can match now Sam with Elvis. As we can see, we've got a complete matching. This complete matching is not necessarily unique. So if we looked at this point right here, I could actually swap Dad and Sam over as one possible example. I could swap Mum and Sam over as well. So the complete matching is not necessarily unique. We can't always find a complete matching either. So for example now, if Tom said all I like is One Direction and Charlie only likes One Direction, they're going to be fighting for it. Therefore we couldn't get a complete matching, and we would look for a maximal matching. Another example of that might be in a workplace. We might have 4 workers matched to 5, or 4 workers who could now go to 5 different jobs. If we got 4 workers and 5 jobs, one job is going to go unmatched. As you've just seen, I've found a complete matching. Clearly we could experiment with combinations and look for complete or maximal matchings. So in this case, it was nice and straightforward. For more complex scenarios, we would look to employ what we call the maximum matching algorithm to find the best possible scenario or scenarios. So as you can see, it's not always the case that we're going to have a unique complete matching. This is just one. So what we're going to do now is go on and look at the maximum matching algorithm. So what we're going to do is start with a typical question. We're told the tour director of a museum needs to allocate 5 of his guides to parties of tourists from France, Germany, Italy, Japan and Spain. The table shows the language spoken by the 5 guides. So Ruth, Steve, Tony, Ursula and Victoria. Ruth, French and Spanish. We've got now Steve, German and Japanese. In part 8, we're asked to draw a bipartite graph to model this situation. We're told the director allocates Ruth, Steve, Ursula and Victoria to the parties who speak the first language in their individual lists. And then in part B it says, starting from this matching, so this would be an initial matching, use the maximum matching algorithm to find a complete matching. Indicate clearly how the algorithm has been applied in this case. So let's go ahead, and again, you'll probably get some form of graph or some form of template to do this bipartite graph. So what we're going to have then are 5 different people. So I'm going to have set X are going to be the people, and set Y are going to be the languages that they speak. So initially, we're just going to show the possible combinations on a bipartite graph. So let's just put this up, and I could just copy across. I'm going to be very lazy and then do something like this. So let's label these up. All of these letters are different, which is going to make my life slightly easier. So we're going to have R, S, T, U, V. Often you'll see that these are just parts of the alphabet. So R, S, T, U, and V. And then what have we got here? Let's just do these. Let's say French, Spanish, German, Japanese, and Italian. Do check that you've got them all. Okay, so let's start off now, and what we'll do is just show this on a bipartite graph. This isn't yet an initial matching. I'll show an initial matching shortly. So Ruth now speaks French and Spanish, so let's do that. Ruth is French and Spanish. We got Steve, German and Japanese. So Steve, German and Japanese. We've got now Tony, French and German, so French and German. We've got Ursula, Spanish and Italian, so there's Spanish and there's Italian. And then we've got Victoria, who's Italian, Spanish, so let's do Italian. We've got Spanish and Japanese, so up to Spanish, up to Japanese. Now, if you're dealing with a problem where you're trying to find a complete matching or a maximal matching, seeing it in this form is not always easy, and that's why I like the table. So what we're going to do is go ahead and consider now implementing or carrying out the maximum matching algorithm. The first step is to consider what we call the initial matching. Now what we've got down here is Ruth, Steve, Ursula and Victoria are now matched to the first one in their list. I could show this on here. Again, it might get a little hectic, so I'm just going to scribble now a new initial matching. So what I'm going to have is the following. So here are my nodes, and I'm just going to quickly scribble these on and look at the initial matching. In an exam, you will be given this. So what we've got then is RS, and then we've got T, U, and V. We've got the languages F, S, G, J, and I. So what we're told is they are initially matched, and we'll do this, they're initially matched to the first in the list. So Ruth is matched with French. We've got Steve matched with German. Let's put Steve to German. I've got S and S here. You might want to just change those for ease of use when we come to the matching. If you want ST and SP, in fact, I'll do that just so it's a bit easier for you to see. So we've got ST and then we've got SP. You can, of course, work off this. Don't for one moment think that you have to do this initial work. To begin with, I just want to show an initial matching on a fresh bipartite graph. So now we've got Ursula. Ursula is matched to Spanish. So let's go Ursula to Spanish. That's the first in a list. And Victoria is matched to Italian. So let's grab Victoria. Victoria is matched to Italian. So what we can see here is this is an initial matching. We can see at the moment Tony is not matched. Japanese is not matched. We can't send Tony to Japanese because he doesn't speak the language. So what we do is look now at the second step of the maximum matching algorithm. The second step is finding what we call an alternating path. An alternating path starts with one unmatched vertex in X and ends with one unmatched vertex in Y. So what we want to do is find now a route that takes me from Tony to essentially Japanese. And the way we do this is to consider matched and unmatched, and we'll start looking at the notation. So what I'm going to say then, using an alternating path, and alternating paths are also not always unique. You might find that there are a whole host of them. So what we're going to do is do the second step of the maximum matching algorithm. Now, Tony, if we look at Tony, Tony could be matched to French or German. So what we're going to do is decide on which of these. We want to finish at Japanese. Often you could look ahead. So for example now, if here, let's say, in fact we've got Steve here. If we look at Steve, Steve does speak Japanese. So what I'm going to say then is now that Tony is not matched, and this is the symbol that we use. This is unmatched. He's not yet matched to German. German at the moment, if we look here, is matched to Steve. So German is matched to Steve, and we use now the equal sign. So unmatched, matched. So that's matched to Steve. Now Steve could be matched to Japanese, and this is one alternating path. So I can say now that Tony is not, but could be matched with G. G is currently matched with Steve. Steve could be matched to Japanese. This is called an alternating path. This takes me from one unmatched vertex in X to one unmatched vertex in Y. If we've got more than two or more than one unmatched pair, we would have to carry out this algorithm more than once. Now, this is an alternating path, and you might often hear the term breakthrough. Breakthrough, not always used, is now saying that I've got a route from T to J. At this stage, we change status, and this is the next part of the algorithm. This is now the maximum matching algorithm. If I change the status, I now match Tony with German. So Tony is now matched with German. I unmatch German with Steve, and now I match Japanese with Steve. Each time we implement this algorithm, we increase the number of matchings by 1. So before we could see now that Tony wasn't matched, Steve was matched, Tony is now matched, and Steve is now matched with something different on his list. So we're told now, it said draw a bipartite graph starting from this matching, use the maximum matching algorithm to find a complete matching. So what I can now do is look at this. So what I've done, I've gone from Tony to German, German Steve, Steve to Japanese. So change status, and that's what we've got. So if we now look, what we can say is Ruth is still going to French. That's good. Steve now has Japanese. So we can put that on. Tony now has German. Ursula still has Spanish. And then on this one, we've got the last one, which was Victoria. Victoria has gone to Italian. So if I wanted to draw this now, I'm just going to go over the top of this. We can see now that we've got R to F, we've got Steve to Japanese, we've got Tony now to German, we've still got Ursula to Spanish, and we've got Victoria to Italian. That is a maximum matching. That really worked out quite nice. That really, really did. And very rarely will you get a case that's as straightforward. Now, I didn't need to do that. It was just that I spotted ahead that Steve spoke Japanese, Tony spoke German. If I can hook Tony up initially with the unmatched German, with is matched with Steve, we could have done that. I could have gone around the houses a bit. So this is not now a unique matching. What I could have done is sent now Tony to... let's have a look how we can do this. Off the top of my head, we could have sent Tony now to French. We know that Ruth was matched to French. Ruth could go to Spanish. Spanish was initially matched to Ursula. Ursula, the Spanish could have now gone to, where could we go from there? Spanish could have gone to Victoria. And then we can hopefully, I'm kind of losing the plot there, but hopefully you can see that there is another possible way of getting back to Japanese. Might even gone one loop on, but you can see that you can go between these. So STJ is not unique. So there we go. That's an example of now finding a complete matching. So what we've done is stated the initial matching, and we'll be given that in the question. We then look for an alternating path. An alternating path starts at an unmatched node in X and now creates a path to an unmatched node in Y. If we need to carry this out more than once, we certainly can do. We then write it out. We look for the link, we change the status. Every time we change the status, we increase the number of matchings by 1. Okay, let's look at another scenario. Me talking through that one was pretty poor. So hopefully you can see that if you really wanted to, you could look for another alternating path. I generally want the shortest one possible. Okay, we're told the organiser of a sponsored walk wishes to allocate each of 6 volunteers, Alan, Jeff, Laura, Nicola, Philip and Sam, to one of the checkpoints along the route. 2 volunteers are needed at checkpoint 1, which is the start. We've got, and it says 1 volunteer each of checkpoint 2, 3, 4 and 5, which is the finish. Each volunteer will be assigned to just 1 checkpoint. The table shows the checkpoints each volunteer is prepared to supervise. So in this case, we've kind of got jobs again. So Alan can go to 1 or 3, Jeff 1 to 5, Laura 2, 1, 4, etc, etc. Initially, Alan, Jeff, Laura and Nicola are assigned to the first checkpoint in their individual list. In part A, we asked to draw a bipartite graph to model this situation and indicate the initial matching in a distinctive way. So I'm just going to draw 2 bipartite graphs. Starting from this initial matching, use the maximum matching algorithm to find an improved matching, clearly list any alternating paths used, explain why it's not possible to find a complete matching. Okay, so if we consider now, why is it not possible? Let's have a look. If we consider here, if Sam is matched to 2, let's just say Sam was matched to 2, that means Philip would be matched to 5 and Nicola would go unmatched. If Nicola was matched to 5, Philip would have to take 2. If Philip takes 2, Sam can't take anything. And some articulation of your answer would be perfectly fine for that last part. Okay, so let's go ahead. Let's do now our bipartite graph. So I'm going to use these. Generally, a scribble would be perfectly fine. We've got a slight different scenario here, though. We've got now 6 people and we've got 5 checkpoints. So we're told that 2 people are going to checkpoint 1. And I'm going to show that by having 1A and 1B, okay? Ideally not 1, 1 and 1, 2. We'll just keep it 1A and 1B. So that gives me now, how many have we got? We've got 6, and then we'll match that up. So let's do, and I keep using the word match. Be careful. As we've seen, a matching, it's not as we would use it in the normal sense. So let's put these on, and what we'll have is AG. So this one, AG, we've got L, N, we've got P, and we've got S. So what I'm going to say is that this is going to be 1A, we've got 1B, 2, 3, 4, 5. Remember, a 1-to-1 is, or a matching must be a 1-to-1. So let's go for this. Let's look now at Alan. We'll put Alan on here. Alan can go to 1A, he can go to 1B, he can go to 3. So that's showing where he can go. Jeff can go to 1A, he can go to 1B, he can go to now, what have we got? 5, haven't we? 5. Okay, Laura 2, 1, 4, so Laura can go to 1, so 1A, 1B, she can go to 2, she can go to 4. Okay, let's look at Nicola. Nicola is less flexible, so let's send Nicola just down here. We've got Philip 2 or 5, so 2 or 5, and then we've got Sam at 2. As you can see, these graphs get quite cluttered. You might, if you wish, for your own benefit, actually write here now 1A, 1B, and then 3. Here 1A, 1B, and 5. Here 1A, 1B, we've got 2 and 4. I'm not suggesting you have to, but it might be an option if you're slightly unsure. Okay, so there's our bipartite graph, and we're going to indicate an initial matching. So initially, Alan, Jeff, Laura and Nicola are assigned to the first checkpoint in their individual list. So let me do that, and I'll scribble that just here. So what we'll do, we'll go ahead and I'll just do a quick scribble. So what we've got, again, just put these down here. We've got our 6 people, okay, and what I'm going to do is just put these up. Now the 1A and 1B don't really matter in this case. All we'll do is go with them. So we've got initially Alan, so we're going to have Alan matched to 1A. So we've got, let's put Jeff here. We've got Laura, we've got Nicola, we've got Philip, and we've got Sam. So let's go 1A, 1B, we've got 2, 3, 4, 5. Again, this template would be in your exam. Whether they would give you 1A and 1B is another question, but you can check on that. But just have some idea. So we're going Alan 1A, we're going to Jeff 1B. Could have swapped those over, it doesn't really matter. What else have we got? We've got Laura. Laura is going to 2, hence why the 2 comes before 1 in her list. And then we've got Nicola. So Nicola is going to 5. So what we can see right here is we've got a slightly trickier scenario. So we've got 2 unmatched nodes in X and 2 unmatched nodes in Y. So we're going to start with this initial matching, and we're going to use maximum matching algorithm to find an improved matching. Now, an improved matching, all it means is I've currently got 4 people going to 4 checkpoints. An improved matching of this would be 5 to 5. It doesn't have to be 6 to 6. And we can see that later on we can't find 6 to 6 anyway. So when you're told to find an improved matching, let's even go back as far as the CDs. If my initial matching was Mum to Whitney, if I could then show that Charlie was going to one direction, that would be an improved matching. Okay, so let's go ahead and do this then. So that's our initial matching. So all we can do now is start with either P, so we can go now from P, or we could go from Sam. Both of these are unmatched. So let's consider now Philip, okay? What we can do from here is choose Philip. Now, it might be the case that when you start finding an alternating path, it doesn't work, okay? So at the moment, it might not work. So what we're going to do is do the following. We're going to say now, and let's go ahead, we will now match up. Let's go for, let's do this one. In fact, let's go for Sam. Let's say now our initial matching is given here. Let's now carry out the maximum matching algorithm. So we'll say now that Sam is not matched to 2. Now Sam is not matched to 2, and I've shown that by the line here. 2 is currently given to Laura. So at this stage, now Laura has a choice. So what we can see from here is that 4 is currently unmatched. So all I would need to do is say that Laura could actually now be matched to 4. So if we consider this, what we've got is the following. We've got S, Sam could go to 2, which is matched to L, which could be matched to 4. So what we would say then is our alternating path. So alternating path, this is just one of many different combinations. Alternating path, if you want to write the word breakthrough, you can do. So when we change status, we increase now the matchings by 1. So change status, and what we would have now is S would equal 2, and now 2 wouldn't be matched to L, which would now be matched to 4. So what we could see now is if I did this, and again I could put this on here if I liked, I would want to write these out. So we need to now list the alternating path, and we're going to employ or use this algorithm right here, and I'm going to write out now an improved matching. Now this right here isn't the improved matching. In the last question here, this was now the complete matching. I wrote them out. And now I'm going to write an improved matching. And be careful with this, okay? Because if we just follow this down, remember we've changed them. So if we consider now A is matched to 1A or 1, G is still matched to 1B or 1. We've got now L is no longer matched to 2, L is matched to 4. We've got now N is still matched to 5. P is unmatched, and we need to say that just here. P is unmatched. Okay, and then we've got now S is now matched to 2. So we can see that we've got 1, 2, 3, 4, 5 matches instead of 4. So carrying out the maximum matching algorithm has increased the number by 1. As stated, that is not the only possibility, and sometimes you'll hit a dead end. So for example, now if you wanted to go a different route with an alternating path, say we started with Philip. So what we could do now with Philip here, if I said, well, let's now send Philip to 5, okay? If we think about this, if I sent Philip to 5, if I said now P is now not matched. So I'm matching now one unmatched with one matched. The idea is I link the pair. So what I'm doing is matching one unmatched with a matched. So P to 5. Now 5 is currently matched to Nicola. Now Nicola can't be matched to anything else, so this is not going to work. So we would now start again, and you can of course look ahead in advance. So with the maximum matching algorithm, what we do is start with an initial matching. We're trying to link up now the unmatched node or nodes in set X with the unmatched node or nodes in set Y. We start off by choosing one of the unmatched nodes in X. Could start with Y. I prefer to start with X in this particular case. We would then find one that it is matched with. We would say now P, in this case I've done S. S could be matched with 2. 2 is currently matched with L. L could be matched to 4. We then change the status. Changing the status increases the number of matches. I've gone from 4 to 5. As you can see, it doesn't always work out, as that was a very bad choice. Yeah, if I sent Philip now to 2, and we sent, for example, and I'm not going to go through this because I did the last one in my head and it didn't really go too well. So as you can see, you've got lots of opportunities here. You could send now. You could have started off with Philip to 2. So we could have gone Philip to 2. 2 is L. L is back now to 4. So there we go. Explain why it's not possible to find a complete matching. I did that at the start. If we consider now, we've seen with the bipartite graph, if we gave Nicola 5, that would mean that Philip would have to do 2, which leaves Sam unmatched. So there we go. We've looked at complete matchings. We've looked at a maximal matching right here, and this is a maximal matching. If we've got 6 nodes and we've matched 5, or 6 on each set, and we've matched 5, then that is a maximal matching. We can't find a complete matching, therefore we have to settle with 5. And there are, of course, different combinations. What we'll do just to finish is actually go back to my first scenario and employ now the maximum matching algorithm to this. And what I'll say is initially, so let's look at initially, so let's go for initially now, we will give some matching. So let's make some up. Let's say that C is matched with O, so C matched with O. We will say now that on this one, what are we going to have? Let's say that M is matched. Let's say M is matched with, let's go for E, okay? And then we will say, let's do one more. Let's say now that T, so T is matched with J. So I'll kind of make this up as I'm going. And when we can show this and just now simply employ the maximum matching algorithm to find a complete matching. So let's scribble now a bipartite graph and show this initial matching. So what we'll have is something that looks like this. So we've got these 5 vertices or nodes. We've got Mum, we've got Dad, we've got Tom, we've got Charlie, and we've got Sam. We've got now O, that was One Direction, we had Whitney, Elvis was it, Jay-Z, and then we had I. So my initial matching, let's do this, let's say that C is matched with O, okay, and then we'll do M with E, so M is E, we've got T with J. So we can see now that we've got Dad unmatched, we've got Sam unmatched, and we've got Whitney and Iron Maiden. Okay, so what we're going to do now is look at the list, and I'm going to choose, and this is why I think using this is slightly harder. So let's go back to this without the orange bits on. This now is our bipartite graph, and this is why I prefer it like so we can see it in here. So it might give this information. It'll probably take you 10 seconds, 20 seconds to just write these out and just see which are which. Don't have to, but it's an option. So what we're going to do now is the following. We're going to start off, and I could start anywhere. I could start with Sam, or I could start with Dad. I'm going to start with Dad. So what we can see is Dad is matched, and in fact, let's just grab this down, and we'll move this down as well, so we can now see what we're doing. So if we just put this down here, and we can see where we're going with this. So what we're going to do is look now at putting this information in. So this was the initial matching that I gave myself. So initially, these are matched like so. So let's start with Dad. Let's just see an alternating path. So what we'll say then is the following. Dad is not currently matched. We want to get now to W or I on here. Now, quite clearly, I could just say, well, we're going to go to I, and that would be now a matching an unmatched with now a match. I'm going to make it slightly harder. As you can see, making this one up, we could just link these pairs up. But what I'm going to do is go through this to look at different alternating paths. So what we're going to say then instead is Dad is not yet matched. What I'm going to do is match him up now with E. We can see in his list he can have E. So he's not matched with E. Now, at the moment, Mum is matched with E. So we can see that Mum is matched with E. So we'll put that there. Now, let's look at her list. She can be matched with W or E. So what we're going to do is say now that she can be matched with W or E. So what I'm going to do from here is say that now she could be matched with the W. So here is an alternating path. Okay, so here's an alternating path, and as stated, you could have just connected these two up. That's not the idea of what I'm really looking at. So what we'll do, we'll state we're going to change status. So change status. So that gives me now D is going to be equal to E. Then we're going to have M is equal to W. So D and E are unmatched. E and M are matched. M and W are unmatched. Now, when I've employed the maximum matching algorithm, D is matched with E, M is matched with W. So if I wanted now, I could write out an improved matching. So the improved matching, which I'll write just here, Mum is now with W. We've got Dad is now with E. We've still got now T, and Matt with J. We've got C, which is with O. And then we currently have S, which is unmatched. So this is an improved matching using the maximum matching algorithm. Quite clearly, I would never use it because it's blindingly obvious to see what we need to do. But it's just showing you how you can do it. So this is the current scenario. So what we need to do now is employ the maximum matching algorithm again, because S is unmatched. So instead of being obvious and sending S to I, what I'm going to do is look at this again. So if you wanted, you could draw another bipartite graph. You certainly don't have to, but it is an option for you. So if we look at our updated matching, and you will be working on the updated matching when we employ it again, we've got Mum, we've got Dad, we've got Tom, we've got Charlie, we've got Sam, and then we've got these right here, which we've got O, W, E, J, and I. So our updated matching looks something like so. So let's do an updated matching. Mum is with W, D is with E, we've got T with J, and we got C with O. So what we're trying to do now is match an unmatched node in X with an unmatched node in Y. So we start off by going from S to one of the matched ones. So let's look at our table, and we'll do now another. So let's grab this down and we will move that. Let's just put that there for now, and we will do this again. So at the moment, this is what we've got. So what can I do? Well, I want to get to I. So what I could say then is the following. We could say that S could now be matched with E. The reason I'm doing that is I can see Dad can go to I, and that's going to complete my matching. So we would say now the unmatched with now going to the matched one. And the matched one is E. So I'd say S is unmatched with E, which is matched with D. D is not matched with I, but could be. And that is another alternating path. So alternating path. Okay, change status. So change status. And we would now have S is equal to E. And now D is equal to I. So we could see that S was matched with E. E was no longer matched with D. And then D was now matched with I. So let's draw our final bipartite graph, and we will show this. And again, this isn't necessary. I'm just giving you an idea on how you could have employed this a second time if required. Not required in this one, as we knew what it was, but it's good to get a little understanding and a bit of practice. O, W, E, J, and I. So let's do this. So what we're going to have then is the following. We need to be careful with this. So let's do these first. So this is going to be S to E. We've got D to I. We've still got from the original one, or the one before, we've got M to W. We've got now T to J. And we've got now C to O. So just to state our complete matching, in this case, we can see now that M is equal to W. We can see that D is equal to I. We can see now that T is equal to J. We can see that C is equal to O. And we can see S is equal now to E. If we look at that, that is yet another one. Now my initial, if we went back to my initial one, what did I do for my initial one? I can't even remember what I did. But as stated, it was, in fact, here it is, isn't it? This was the original one. So D to I, S to E, M to W. So have we gone back to the original? Yeah, so there we go. That's just yet another way of showing this. And of course, you could swap some of these over if you like. So for example, now if you wanted, you could go Sam to W and then M to E. So another configuration, let's just do a swapsy. M might want to go to E, and then we could do S to W, okay? And it will look something like that. So that's another one. So there we go. That's matchings and using the maximum matching algorithm. As I say, I've gone at this a bit sort of as I go, so hopefully it's given you a bit more of an insight, but that should provide enough information for you to tackle the vast majority of exam style questions.